This is our work, clever ordering of transactions on AMMs. And at a super high level, because I want to save us some time for maybe some questions. Here's the idea. We've talked a lot about MEV mitigation strategies, and they generally fall into three different categories. Okay. We talk about MEV comes from the idea that a block builder has the exclusive authority to insert, censor, or reorder transactions. And what we say is, why don't we fix an ordering? Okay. And so far, the proposals on fixing and ordering seem to fall into these categories. Okay. You can do it randomly. And that's one option. You can do a gas priority auction. That's another option. Or first come, first serve. And first come, first serve, it's interesting, definitely. I mean, a lot of popular markets do implement that, but it has its own issues, like racing for access, co-locating geographically, and all of this. So instead, we're going for an interesting fourth option, which is, what if we can enforce a social order? We imagine there's like a social planner that can enforce an ordering that's good somehow. So now we actually get public benefit out of this, and we can mitigate MEV extraction a little bit. So here's the general idea. So we're imagining we're doing this on AMMs, and recall that on an AMM, every single transaction has some price impact. The price updates continuously as you trade. And here I show 4 transactions, and we can sequence them in different orders. And the order matters because the price that each user is given is impacted by the trades that were sequenced before them. So we figure, why don't we optimize for volatility? And we've considered other economic goals, for example, equality or something like that. But it's not really clear exactly how you would even define that, nonetheless, whether it would be good. But volatility seems to be, I don't know, fairly acceptable. So what we say is, let's imagine a social planner is trying to minimize price volatility. And in other words, they're basically trying to keep the price around a certain set point. We imagine this set point, probably a fair set point to pick, is the price that the AMM, the spot price of the AMM at the start of a block. Probably because users most likely observed this price when they went and signed their transaction, so they consider it acceptable. So here's how that might look if we organize transactions in order to have some sort of minimizing volatility. So we basically just see if we can hover around this price. Okay. Here's an interesting contrast. So I generated some transactions, and I just permuted them, just brute force, tried every single different ordering. And here I've drawn for you the ordering which maximizes the volatility and minimizes the volatility. And again, this is all within one block. So here you can sort of see that, that difference illustrated. Now, doing this by brute force, by looking at all the permutations, is obviously undesirable. Okay, that's not great. So instead, what we do is we develop an algorithm we call Clever, which is the clever look ahead volatility minimizing rule. Okay, that's fun. So here's what we do. We say, well, we know how to compute volatility. And at each step, when we're picking what is the very next trade that we want to sequence when we have our mempool of trades, we pick the one which has, in a single step fashion, the smallest contribution to volatility to offer. And that's the trade that gets sequenced next. We find that it has one interesting property in that it actually prevents sandwich attacks. So that's already great, number one. Number two is that we find that even though it doesn't necessarily get you the optimal organization that optimally minimizes volatility, it still gets pretty close in most cases. And so that's really interesting. Then we actually study what are some second order effects that happened. What would be, we imagine, what are some changes to trading strategy that might occur if people are subject to this type of rule? Actually, I'll go here. So one of the focuses we do is trade splitting. So this is interesting. We want to actually encourage trade splitting in this situation. So if you're doing a large trade, you're going to have a large price impact on the AMM, which is bad for volatility. Instead, we want you to break up that trade into several smaller trades, which ideally the system can interleave between other people's trades in order to maintain volatility a little bit better. And it turns out that this is incentive compatible with that. So what we do is we find that if one trader splits and nobody else does, that single trader has an expected increase in amount out or a slight price improvement subject to this rule. Then we find that if everybody splits, everybody also receives a slight increase in amount out or a slight price improvement. So that's great too. The second effect that we observe, and this is maybe for planners who are planning blockchains and setting things like trading frequency or how long you wait in order before you produce a block. We've heard a lot of talks talking about how short block times are awesome. In this situation, it's actually interesting because if you wait for a longer block time and you accumulate more transactions, you can actually organize them in order to minimize volatility within that block. Now, of course, it's going to have some impact on price discovery, which we don't really explore, but you might imagine that there's some trade-offs there.
Is the effect of this ordering you have similar to the effect of netting?
Sorry, I'm not familiar with that.
If we can keep questions to the end.
It might be, yeah. So how about let me explain this graph and then I'll talk about that. So and this will be very quick, I promise. So on the x-axis here, what we have is block size. So we generate a script of 100 synthetic transactions, and we imagine that we're going to be sequencing them as if they arrived in real time, one by one. And so first we imagine all the way on the left here, what if we sequence them one transaction per block? In other words, first come, first served. We have no ordering power here at all. Versus all the way on the other side, where we say they all go into one big block, okay, with 100 transactions. And we find basically that the volatility is reduced significantly. Okay, that's not surprising because we're doing this sort of social planning, right? Okay, so that's basically it. Here's a link to our paper.